So in this video, I'm going to be talking about the GS test. And the GS test basically states that if you have some series that is of the form a times r to the n, you can take that r and get the absolute value of that. And if the absolute value of that is less than 1, then it converges. Otherwise, it will diverge. You can also find the exact value to which it converges by using the formula a over 1 minus r, where a is the first term in the sequence. And that's another reason why r cannot be 1, because it gives an undefined result for this expression. And we already know r can't be negative 1 because you get some oscillating thing. And these numbers make sense, especially if you draw the graph. And you draw the graph of something in which the r is greater than 1, then you'd get some exponential that goes all the way to infinity. But if your r is between 0 and 1, you get an exponential decay that goes down to 0. So for all the problems I'm about to cover, I encourage you to pause the video and do them yourselves before seeing the solutions. So let's look at a simple example where we have the partial sum is 1/3, 1/9, 1/27, and 1/81, etc., etc. We can see that clearly they scale by 1/3. So we can have our a represented by 1/3 and our r also represented by 1/3. And since the absolute value of r is less than 1, it's equal to 1/3. So we know that our series converges. We can find out what number that converges to by using the formula a over 1 minus r. In this case, a is 1/3 and r is also 1/3. So we can simplify that to 1 over 3 minus 1, and that's just 1/2. So we can use that to work with these three simple examples. So for the first one, we can extract the a and the r. So in this case, the r is 2. The absolute value of 2 is just 2, and that's greater than 1. So we know that it diverges. For the second example, we can take out the 3, and then we're left with 1 over 2k, and we can factor a k out of the 1 over 2k to get the r, which is 1 over 2, and that's less than 1, so it converges. For the final example, we can see that the a is just pi and the r is e over 3, and e is approximately 2.7, and 2.7 is less than 3, so the absolute value of r is going to be less than 1. Again, it converges. If you're asked to find the exact value of convergence, you can just use the formula we learned earlier, a over 1 minus r, and get the first term, so it's evaluated at 0, so 3 over 2 to the 0. And then just plug in the r, and we get 6. For the second example, it's just going to be pi times e over 3 to the 0, and that's just going to be pi over 1 minus e to the 3, and you can simplify that. For this example, you can see that all the terms are changing by a factor of negative 1/4, so you can make that your r, and since r is negative 1/4, the absolute value is going to be less than 1, so our thing then converges, and you can find the exact value at which it converges by using the first term over the 1 minus the ratio, and you can get 80 over 3 times 1 plus 1/4, and inside the bracket I guess is 5/4, so you can simplify that. It'll be 80 over 15 over 4, so it's going to be 320 over 15, and that's just 64 over 3. For this one, you're going to have to do some work to get the ratio. So for the numerator, negative 3 to the k plus 1, it can be represented as negative 3 to the k times negative 3. Similarly, 4 to the k minus 2 can be represented as 4k times 4 to the negative 2. And there you can pull out the r, which is going to be 3/4, which is less than 1, and therefore it converges. You can use the same formula before to get the exact value of convergence. So if you work it out, you should end up getting negative 196 over 7. For 5 to the k plus 3 over 2 to the 3k plus 1, we can extract the 5k and the 5 to the 3 out of the numerator, and then for the denominator we can represent 2 to the 3k as 8 to the k, and then we can get the r, which is going to be 5 over 8, and that is less than 1, so it converges. Again, you can use the formula to get the exact value of convergence. Plug in the term of the sequence at k equals 0 and the 1 minus r, and you should be able to get 500 over 3 as your answer. So for this example, we just have to simplify the denominator a little bit, and we will get 3n 3 to the n times 3 to the negative 1, and we can extract the r. We don't really care about any other part of it, we just need the r, and it's going to be less than 1, so it converges, and you can plug it into the formula by getting the first term and getting the 1 minus r, and then you can just simplify to get the value that it converges to. So for our last example, we have 2 to the 2n, which we can change to 4 to the n using the trick we did earlier. And then we have 3 to the 1 minus n. Now we can split that up into 3 and then 3 to the negative n. And 3 to the negative n is just the same thing as the whole thing over 3 to the n. So we can extract the r, which is 4 over 3. And in this case, r is greater than 1, so we get divergence. And that's pretty much all there is to it. Geometric series are pretty easy. There are not that many tricks involved.